Good afternoon, dear friends. This lecture is devoted to the study of distortions that may occur in circuits with distributed parameters. We will learn about the existence of two types of distortions, amplitude and phase. We will learn about the causes of these distortions and about the requirements that a line must need to avoid distortions. However, in the beginning, let's briefly review the contents of the previous lecture. In the previous lecture, we studied the speed of propagation of voltage and current waves in line with distributed parameters. We learned about the existence of two types of propagation speed, phase velocity and group velocity. The phase velocity determines the speed of propagation along the line of a constant phase of oscillations. As we discovered, this velocity depends on the frequency of the oscillation. The higher the frequency, the greater the speed of propagation of a certain phase state of the wave. The phase of oscillation is not a material object, so there is no prohibition on it moving at a speed that exceeds the speed of light. At the same time, a single sinusoidal oscillation cannot carry information. Information can be conveyed not only by the sinusoidal oscillation itself, but also by its change, such as an increase or decrease in amplitude. Such oscillation, which change the amplitude, is already non-sinusoidal. But as we remember from the lectures on circuits on non-sinusoidal AC current, such oscillation can be represented as a sum of several sinusoidal oscillations of different frequencies. Thus, we already have not one wave, but a group of waves, so-called wave packet. The propagation of a wave packet is characterized by the group velocity, which can never exceed the speed of light. However, in the presence of waves of different frequencies, with different phase velocities, distortions of the signal shape that propagates in the line may occur. The study of these distortions and their clarification will be the subject of this lecture. Let's assume that the input signal on the line is a series of rectangular pulses with an amplitude of 100 volts and a period of 200ths of a second. We know that this signal can be decomposed into a Fourier series using the formula provided here. As we can see from this formula, the Fourier series expansion consists only of odd harmonics. Let's limit ourselves to the first three harmonics of the Fourier series, the first, third, and fifth voltage harmonics. This formula is shown here. As we can see, the amplitudes of the third and fifth harmonics are smaller than the amplitude of the first harmonic by a factor of 3 and 5 respectively. And the initial phases of all three harmonics are 0. The sum of the first three harmonics of the Fourier series is shown in this figure as a red curve. Here is this curve. Remember, this voltage waveform is at the input of the line. Next, we will consider how and why this waveform will be distorted during signal propagation along the line. Consider the first type of distortion. We talked about the fact that at the input of the line, the signal has such a shape. Let's see what our signal will look like at the output of the line. As we know, it takes some time for signal to travel from the beginning to the end of the line. This time will be shorter the higher phase velocity of the signal, which is directly proportional to the frequency. Therefore, we can say that the zero phases of the fifth harmonic signal will reach the end of the line early than the zero phases of the third harmonic signal. The first harmonic will arrive at the finish last. That is, when the zero value of the phase and therefore of the signal of the first harmonic itself reaches the end of the line, there will already be some non-zero values of the signals of third and fifth harmonics, as shown in this figure. Observe, in this figure, the dotted line indicates the moments in the time when the sine wave of the first harmonic has a zero value at the output of the line. However, at this moment, the sine waves of the third and fifth harmonics at the output already have some non-zero values. It's clear that as a result of superimposing all three harmonics components, which have a phase shift relative to each other, we will no longer obtain the same signal shape as was at the input. Therefore, we can say that the output signal is distorted relative to the input because the phase shifts between the harmonics do not correspond to the corresponding phase shifts of the input signal. But these are not all the troubles what await the signal during its journey along the line. We will talk about this for now. Phase distortion is not the only type of distortion that can occur when a signal is propagated through a line. Let's take another look at this figure. For the sum of several sinusoids to form of signal of a certain shape, certain phase relationships between them are just one requirement. Another equally important requirement is to maintain the amplitude relationships of this sinusoidal oscillation during propagation. As we can see from this formula, the amplitude of the third harmonics in the Fourier series expansion is 3 times smaller than the amplitude of the first harmonic, main harmonic. The amplitude of the fifth harmonic is 5 times smaller, and so on. However, at the output of the transmission line, we will also get a rectangular pulse, but only if the amplitude of the third harmonics is 3 times smaller than the amplitude of the fifth harmonic is 5 times smaller than the amplitude of the first main harmonic. As we already know, the amplitude of a signal attenuates as it propagates through a transmission lines. However, the amount of attenuation should be the same for all harmonics, regardless of their frequency. If the attenuation is different for each harmonics, the shape of the signal at the output will be different from the shape of the signal at the input. This is illustrated in this figure, where the amplitude of the fifth harmonics exceeds the amplitude of the third. Please note that this figure, the relationship between the initial phases of the harmonics is not violated. In our case, all initial phases are 0. However, despite this, the shape of the output signal is distorted compared to the shape of the input signal. In ordinary lines, both the signal attenuation and its phase velocity depend on the frequency of the signal. Therefore, in such lines, two types of distortions occur simultaneously: phase and amplitude distortions. The simultaneous action of phase and amplitude distortions is shown in this figure. From this figure we can see that when both types of distortions act simultaneously, the shape of the signal at the output of the line differs significantly from the shape of the input signal. Thus, when a signal propagates through a line, its shape is distorted relative to the shape of the input signal. Is it possible to make a line in such a way that there are no distortions? We will find out about this now. Thus, the distortion in the line is caused by the frequency dependency of the attenuation factor and the phase velocity of the line. This allows us to say what will determine a line that doesn't have distortions. We will call a line without distortions a line in which the attenuation factor and the phase velocity do not depend on the frequency. It can be shown that such properties of a line arise when such a relationship is fulfilled between its primary parameters. The line resistors divided by the line inductance should be equal to the ratio of the line conductance to the line capacitance. Let's prove that with such a ratio of primary parameters, the attenuation factor and phase velocity do not depend on the frequency. Let's denote each of these relationships with the letter K. This allows us to express the resistance and conductance of the line in terms of its inductance and its capacitance, as shown here. Let's substitute these relationships into the formula for the propagation factor. After some simple transformation, we obtain that the attenuation factor doesn't depend on frequency and the phase factor is directly proportional to the frequency. By substituting this phase factor into the formula for the phase velocity, we can confirm that the phase velocity also doesn't depend on frequency. Therefore, we have proven that if these relationships exist between the parameters of the line, there will be no signal distortion in such a line. Let's consider how a signal propagates in a distortion-free line, for which the relationships between primary parameters are satisfied. To do this, we will again use the first three harmonics, first, third, and fifth, of the Fourier series expansion of a rectangular pulse. The waveform at the beginning and the end of the distortion-free line is shown in these figures. As can be seen from this figure, during the propagation of all three harmonics along the line, their amplitude decreases, but decreases equally for all harmonics, regardless of its frequency. A phase shift also occurs. Look at the beginning of the line, this figure. All harmonics had zero value or zero phases at t equal 0. At the end of the line, the zero value of all harmonics occur later, at around approximately 0.002 of a second. This is the time it took for the signal to travel from the beginning of the line to its end. But this time is the same for all three harmonics, because their phase velocity is the same. Therefore, at the end of the line, they will also have zero value at the same moment in time. The shape of the resulting signal, red line, has not changed, so there is no distortion of the signal in our line. And now we can make some conclusions. First of all, we can say that in ordinary lines with distributed parameters, the attenuation factor and phase velocity depend on the frequency. Therefore, with a non-sinusoidal signal in the input of the line, its form at the output will be distorted. Distortion of the form of the output signal interferes with the transmission of information over the line. Therefore, such distortions are harmful. To get rid of distortions, signal of different frequencies must propagate in the line with the same phase velocity and to the same extent. The line operating mode is called a line without distortion. The operation mode without distortion is achieved with such ratio between the primary parameters exists. In this lecture, we learned about the relationship between the primary parameters of a line in which distortions does not occur. But we not yet know how best to achieve this ratio in the real line. We will learn about this in our next lecture. Thank you very much for your attention. Bye.